Hello and welcome to my show. I'm the Casual Engineer, and today I'm going to have a little chat about something that's very dear to my heart. Anything that's in the electronic field is my home game. It's what I've been doing for many years of my life. Now I'm after something that's come to my attention because there are people who are so busy saying things they just don't know what they're talking about. So let's have a look at GPS. Going to move over to a set of slides which just cover off the points I want to cover on this. I think it's really important that people understand how these things are meant to work. So let's have a quick look at a GPS receiver. And give me a second, I'll find my diagrams. Now I'll just move over to the right screen. I love being on live, always messes up on me. Oh well, let's just start with this very basic idea. We have a group of blocks that represent how the receiver works. The fellow who built this bought a commercial antenna, passes the signal from the antenna through to front end, which then basically down converts the signal, sends it off to something which does all that work at detection, and then passes the output on the Raspberry Pi to do all the calculations. As we go through, I'll try to find out where the compass sits, because that's the topic of this one. Where is the compass in all of this? Let's just keep changing our box around until we get there. Let's just start with the piece known as the low noise amplifier. The signal comes in through the antenna, passes into this point here, and you have a look. We've got inductors, we've got capacitors, we've got transistors. None of these components are designed to act as a compass, and yet there's a few people out there in the certain community who are saying, oh, but it uses a compass. Oh, I've got some news for you. It's not what you're saying. All this thing does is takes an input signal, boosts its signal level up, and passes on to the next section. The second block that he put up there was his filter. The filter component looks like this, and it only does one thing. It takes an input signal. The physical design of these filters is how they work, and what they do is they cut out everything except the area that you're interested in listening to. So the radio signals from GPS sit around about the 1.5 gigahertz band, and that's all this is. It's just a band. You cut everything else out. Now you're focusing on the area where your satellite signals are sitting. Pretty straightforward from this point of view. And inside of a saw, again, nothing in there that looks like a compass. Let's move on to the block diagram for the RF section. This is probably the key here. You can see where the low noise amplifier I just mentioned sits, where the saw fits. The saw is basically that filter I mentioned before. It's then passed through a down converter into something called IF. Now, for terminology for people that don't know, RF means radio frequency, IF means intermediate frequency. We use these mechanisms for a reason. RF can be quite a broad band of signal. What we're trying to do is convert it to one signal point. So the really old receivers in AM and FM, specifically I'm going to focus on AM receiver, we down converted from the 700 to 1.030 megahertz and took it down to one frequency, 455 kilohertz. Design choices when they come up with this idea was simply, if you can down convert to one frequency, the rest of the circuit can now be built without any tune-ups required. So once you set it up, it doesn't require additional maintenance every time you retune. And that's what they've done here, the same thing. It's simply designed to pick these values and enable you to work with them. All right, once it's down converted, it goes through a series of filters and comes out the end here. Basically, it's a differential. Pretty straightforward. And that's passed on to the next section. Now, I need the next bit. I'm going blind in my old age. The complete schematic. Inside of here again, we can see where the RF goes in, we can see where our local oscillator comes in, our mixer. You can see our down conversion here. Now, I know some people are not electronically minded, so I'm just going to help you a little bit with it by drawing a couple of quick lines. Here it says P1 and N1. And it's not obvious, but these wires actually run to this point and this point, and then onto these 2 points. When you're reading the schematic, you actually have a bit of jumping around to do in your head. I'm used to schematics like this with dozens of pages where page 1 would flow onto page 2, page 3. And this is basically it. These 2 signals come out as differentials. They're passed on to a little filter and then passed on to the next amplifier. The output of that is then fed to a filter in the next stage. So there's 3 stages, 3 sets of filters. Take note, that filter there is adjustable. The whole idea of having adjustable filters so you can actually tweak it to make it work better. To take into account your component tolerances. Every component has a tolerance. If you don't take that into account, this won't tune up properly, and the output, which you're trying to get over here, won't be won't be at the correct signal strength. It might be distorted, it might have harmonics, and you haven't cleaned it up properly. So you make these things adjustable. And not one component in here is a compass. So people have been saying it uses a compass bearing to get something. Got some news for you. That's not the case. Let's just go to a completely blank slate. Nice new whiteboard. One more point I need to really bring up with this. I know it's pretty technical, but antenna design. If you build an antenna that consists of a simple dipole like this, that could be on the roof of your car, it could be mounted on the roof of your house. The signal comes out of this thing in a series of horizontal, and it's classed as a circular pattern, a bit like dropping a pebble in a puddle. It just emanates out from that central point and just goes outwards. And it has no idea what direction. If the signal comes in from this direction, or is going out in that direction, the antenna is completely oblivious to it. There is no feasible way for that antenna design to ever give you a direction. So conceptually, if this thing receives it from any angle and you're now starting to talk GPS, this antenna will see a signal coming from one signal source on this side, one signal source coming in from this side, one signal source coming in from behind, and it won't know the difference. All it will know is that the signal is at, for example, minus 70 dBm for this one. As you can see, I'm writing really well today. Actually using my mouse instead of my pad. So basically, this is pretty much it. This one might be at, say, minus 80. The only thing that the signal strings tell you is roughly what you might think the distance is. But the dBm values are never used in the calculations. What actually happens on the ground is you've got a clock. It's called the real-time clock. It actually keeps track of the date and time and takes the signal after it's been processed through all those stages and simply looks at the real-time clock and the signal that said I sent something at a certain time, and it works out the differential at the delta t. That's it. Now on one satellite, it kind of guesses that it probably took 13 microseconds to reach. Once it gets 2, 3, 4, these delta t's start to become better. And as I heard Wally say, this is all about resolving multiple signal sources and coming up with the delta t to get to each one. It comes back to the principle we keep mentioning to everybody. They don't measure angles, they measure distances. That's it, nothing else. No requirement for this machine to have a compass in it. Just because a phone's got a compass in it doesn't mean the GPS uses it. In fact, it doesn't use it, and I can remember seeing one of these devices back in the 90s when I was working in electronics, and they didn't have a compass on. But they did give you the date, they did give you the time, they did give you your GPS location and your altitude. That information was visible in the 90s. These things were designed back in the 60s, I think. So this is pretty old technology, still being used today, but we've just improved it and made it work better. Now, I do have a live feed. I know there's a delay between when I say something and other guys show up. Hey, Tortorico. Hey, Peter. It's nice to have a couple of people on board today, and I do know that I do have a delay set deliberately just in case there's a couple of things I want to fix up. I usually don't see it unless I look at my channel to see what's going on. So guys, if you've got any questions, start posting them. Yep, 360p. As far as I can tell, my end looks like it's actually transmitting much higher than 360p. So don't know what's happening there, but yet we've all noticed that there are some issues. I've had to put an expander on the volume to try to make my voice a lot louder through the phone I'm using. Ultimately, I don't believe the GPS uses a compass for the simple reason it's not present on the schematics of the device that actually works. I've worked with these units, I've looked inside them, I've seen what's in there, and none of them have a compass in them either. So to the people who are saying they've got a compass, I've got some news for you. If you have been doing that, well, there's this little sketch which I think will sort of sum it up pretty well. Goes something like this. Well, now I'm back to the host frame. I know what just happened. I didn't actually show the scene. That's the thing. That's the fun with being live, isn't it? In any case, that's it. I've pretty much covered it. The people who are saying this stuff are not showing the electronics. None of you have described any of the schematics, none of the block diagrams. You haven't actually sat down with that information and said, there's a compass. You can't point your finger to one. You can't find one. There isn't one. So guys, there's another video coming out in a couple of hours and I will be reviewing that individual very, very happily, memeing him like the fool he is. Okay guys, thanks very much. Thanks for watching and listening. It's time to go. Have a very good afternoon. Have a very good Sunday if you're over this side of the world. If it's your evening, have a good evening. Wherever you may be, keep safe.